Welcome, everybody. I'm Pablo Halpern, and we're talking about user-defined literals today. Literals. In the dictionary, a literal is defined with one of these definitions, and they're all basically, things that are to be taken at face value, right? That's a literal. That's what literal means. But the funny thing is that literal is an adjective. There was one noun definition of literal in the dictionary that I found, and that was this typographical error in usually in a single letter. That is not what I'm talking about. Okay, in C++, a literal is this token that represents one of these things, an integer, floating point, character, a string, Boolean pointer, or a user-defined type. And the user-defined types is what we're going to be talking about a lot today, but not exclusively user-defined types. So we have examples in C++ of literals. Integer literals you got with plain old 1, 2, 3 is an int with the u suffix. It's an unsigned. LL long long, UL unsigned long. We got floating point literals. They have their suffixes for long and float. Character literals, they have a prefix for the L for wide characters, the lowercase u for UTF-16, and the uppercase U for UTF-32. String, again, with the same prefixes. This U8, you're gonna have to forgive me that I don't have my little red laser dot, but this U8 is new in C++20, and that gives you UTF-8 encodings. Do we have any water here? And we have Boolean literals, true and false. Those are the only ones. And we have exactly one pointer literal, null pointer. And what we're going to be talking about today are these user-defined literals, things like minute, big int, regexp. I'm not going to talk about how to write these things exactly. I'm not going to tell you how to implement a big int. But people have been implementing big ints for a long time. Thank you very much. So today we're going to be talking about what is a literal. I think we got that covered. What are user-defined literals and why do we have them? How you define them? We're going to talk about use cases and pitfalls. I'm going to try and focus on the last two as much as I can. So even though we're going to go through all of the mechanics of building user-defined literals, I'm going to be talking at breakneck speed because I have a lot of slides and not enough time. So you'll be getting, the slides will be available after this talk, after the conference is over, and you can look in more leisurely pace at them. But I really want to focus on the examples, the code examples, and so on. All of the examples are C++ 17, unless I say otherwise. Now, please hold your questions to the end, because like I said, I have a lot of material to cover. But if I say something that is completely confusing to you, or wrong, then please do interrupt me. A little bit about me. This is my beautiful self. That is my sexy Prius. I don't know, people think Priuses are nerdy. I don't know what it is. I unfortunately no longer have a C++ license plate because I moved away from New Hampshire, and Massachusetts has different punctuation rules and they won't let me put a plus in there. I am this is the seventh year I'm presenting at CppCon. It's my 8th talk. And like I said, I've got this nerdy car. There's a book coming soon. This year, right, John? Okay. Called Embracing Modern C++ Safely. I'm a contributor to this book. I'm not on the cover, but I am sort of a ghostwriter for a couple of the chapters, including the one about user-defined literals. There are several other talks. One thing that's not mentioned in this list of talks is yesterday's talk by Vittorio, who talked about lessons learned or experience with C++. What was the title of his talk? Say again?
Lessons learned in 11 and 14.
Right, lessons learned in 11 and 14. And it's also material related to this book. And Vittorio is one of the authors on the cover of this book, as you see. Okay, so take a look at and check out these other talks this conference. So now getting into the material properly. What is the user-defined literal? It's a literal whose meaning is user-defined. Simple enough. The value of a user-defined literal doesn't have to be a user-defined type. It can be a native type. But the interpretation of the literal is defined by the user. And when I say user, and this is true throughout this talk, in all of the standards documentation and most books, user means you and I or the library writer, which could be a third-party library or it could be the vendor that sells you your compiler. That's still a user by the definition that we usually use. So the reason we have user-defined literals was to minimize the division between user-defined types and built-in types. Like we already have operator overloading, right? So you have two unsigned values, I and j, and you can compare them if I less than j using the less than infix operator. You can stream them using the left shift operator. And you can do the same thing for string, even though string is not a built-in type. Right? String is a user-defined type by the definition I just gave. And the syntax for comparing them and for streaming them is identical to the built-in unsigned. Great, so that's operator overloading. So we want to do the same thing for literals, right? If you can have a 5u, this is an unsigned literal for a built-in type, why can't we have hello s be a literal for a user-defined type string? And now you can. As of C++11, you can do that. You can't use s in C++11. It's in C++14, it's part of the library. And I'll get to that in a minute. All right, so user-defined literal is basically two parts. The part to the left of the suffix is what I call a naked literal. I invented that term because I could not find any sort of standard or community term for that part of the literal. The naked literal looks just like a built-in literal, any integer or floating point or string or character literal. The part to the right is the suffix, and the suffix is where all the interesting information is. It says what kind of literal this is. If you don't have a leading underscore, that is reserved for the standard library. It's the reverse of normal identifiers, right? In identifiers, if you have a leading underscore and followed by a capital letter, that's reserved for the implementation. And if you don't have a leading underscore, that's yours in your namespace. For literals, it's kind of reversed. If you don't have a leading underscore, only the standard library is allowed to use it. And the compilers I've used enforce that. If you tried to use a literal, if you tried to find a suffix and it's not in namespace std, it would say you can't do that. All right, native literals have suffixes too, as we've seen, for long and unsigned and so on. And so the user-defined literals are sort of trying to mimic that kind of thing. So restrictions. The naked literal has to be a valid literal. You can't invent your own new syntax. It has to look like an int, or it has to look like a floating point number, or a character, or a string. Okay? You cannot do user-defined literals for booleans and pointers, right? And you cannot invent your own syntax. So over here, where you have this 1.2.3, that's no good because 1.2.3 is not a literal. It's not valid syntax for any literal prior to the invention of user-defined literals, so it's still not valid. You can't say null pointer underscore UDL. Well, you can, but that's just an identifier. It's not a user-defined literal. Same thing with false underscore UDL. Now you'll see in this talk a lot, I'll be using this underscore UDL. That's just a placeholder for any user-defined literal. Okay, the suffix is almost certainly not going to be named that. I recommend that you never create a real user-defined literal with that suffix because it'll confuse people, unless you are writing a talk or giving an example or doing a test driver or something like that. One thing that's interesting is that strings can have these suffixes. So what happens, as we know, if you have two normal string literals, one next to the other, they become concatenated by the compiler, and you end up with one long string, as we see in that very first example with the same suffix. If you have a user-defined literal, a string user-defined literal, you would have one or both can have the suffix, but they have to have the same suffix. So the second example, one of them is missing the suffix, that's okay. The third example, they both have suffixes, but they're different suffixes, and that's a syntax error. Now, before we had user-defined literals, we would have things like we would just use the constructor to construct something. So if I had an IPv4 address type, and I was creating, in my program, I needed to name one of these things, and I would say, okay, loop back here, and I pass in the string that it uses to construct the IPv4 address, and you've got yourself something that looks a lot like a literal, but it doesn't use the same syntax. Also, you could always use factory functions. So we have a temperature class, and we have a factory function Celsius that returns a temperature. So again, when we use it, it looks kind of like a user-defined literal. It's a number in your program that builds a temperature. Don't forget these. Just because we have user-defined literals doesn't mean you should use them all the time for everything. These are still perfectly valid and excellent ways of constructing something in your program. So, if we had that, what we just saw, we have these methods, then isn't the user-defined literal just syntactic sugar? Yeah, that's all it is. But, so is operator overloading. In fact, infix operators, even before overloading, is just syntactic sugar. I mean, there's nothing special about A plus B. It just looks like math, and that's why we have it, right? We could have just written plus A comma B. It invokes the plus function on two arguments, all right? So syntactic sugar, don't denigrate it and say it's bad just because it's syntactic sugar. Syntactic sugar is about readability. And syntactic sugar of all sorts can be abused to get something that's the opposite of readable. Okay. So now we say, all right, I have this type, and I want it to look like a built-in type, and I want to define a user-defined literal for it. So how do I do it? The key thing is you're defining this operator. Operator, quote, quote, underscore UDL. Again, this UDL is a placeholder. Use your suffix there. There are 4 different syntaxes for defining it. It's extremely powerful, complicated, and, well, potentially complicated if you get way into it. But very, very flexible because it has these 4 different ways of doing it. We're going to go into each of them in turn, so you don't have to read this whole slide. I'll digress a little bit here and talk about where do you put this operator. Normally, there's an idiom now that has developed that you put your user-defined literal operators in its own namespace. It doesn't have to be one namespace per literal. It could be one namespace for a bunch of related literals. And the reason you do this is because the literal is just this bare word. It's just this, underscore degree or deg thing here. So because when you specify a literal, like 123 underscore DEG, you don't have a place to put in a namespace or any kind of scope resolution. So if these things were all sitting in the global namespace, you would get collisions, right? But by putting them in their own namespaces, we allow this last thing here. You just pull in the namespace of the literals you care about, and then you use them. So in our last example here, this 90 degrees is unambiguous. We're talking about angles, not temperatures. Is that clear? All right, let's finally define our first user-defined literal. We're going to talk first about the cooked UDL operators, which is both the easiest, most obvious, and the most common type of user-defined literal. In fact, in the standard library right now, I'm pretty sure 100% of the user-defined literals in the standard library are cooked UDL operators. So in the book, I call these prepared argument UDLs. After more Googling, even though I did Google it at first, I found that there's beginning to be a consensus around the term cooked. And so I'm going to be using that from now on. The compiler evaluates the meaning, the value of the naked literal before passing it to the UDL. So it does all the heavy lifting for you. You just have to take that value and do something interesting with it. So in this example here, we have the literal. Is everybody here familiar with the tick digit separator for C that was introduced in C++14? I'll be using it throughout the talk. So this is just exactly the same as 1234.5 without the tick. The tick is just there to separate groups of digits to make it more readable. But the tick will come into very interesting use. We'll see both good uses and bug opportunities as we go along. So keep that in mind. So this is exactly equivalent to calling operator quote quote underscore UDL, which is a mouthful, and passing the naked literal in. The naked literal in this case is expressed as a long double. We'll go into that in a minute. There are 12 possible cooked literal overloads for any specific suffix. There's one for a floating point, one for integers. There are 5 for characters, and there are 5 for strings. And the 5 different ones are for the different kinds of character types that we see here. If you end up with, if you express a literal, and it's a cooked literal, and it doesn't fit in the int, or it overflows to infinity, or it underflows to 0, that's your problem. Okay, if it overflows the int, you'll actually get a compile time error. On the compiler, on the Clang compile version I was using, if you overflow to infinity or underflow to 0, you get a warning, which is nice because it is actually valid C++, but you probably didn't mean that. So here's an example. And I should have gotten to this way earlier in the talk, now I realize. Okay, we have a token type. And the thing that distinguishes the token type, it has a value, there's an unsigned, and it could be either an internal or an external token. And we define a user-defined literal for it, which is a cooked literal. So here we have our prototype. It returns a token, and it takes an unsigned long. I feel like I'm missing, oh wait, okay. Yes, okay. And then we use it. Token X, right here. Token X equals 1234 underscore token. That's a user-defined literal. And what that does is it converts 1234 to a unsigned long, passes it into the operator, which constructs a token, which is going to be hard-coded to be internal in the case of a user-defined literal, and returns that token. Okay. If we overflow it, here's a big long hex number. It's longer than fits in 64 bits. It will not fit in an unsigned long on most platforms. So it'll overflow and you'll get a compile time error. Well, let's look at an example of a string literal. Okay. In this case, we have 2 overloads, one for plain characters and one for UTF-8 character strings. Both of them return the same thing. And that's both common and, I should say, it's common to do both things. When you have an overload set of literals, sometimes they all return the same thing because they mean the same thing. And sometimes each one returns something different based on the type that it was instantiated with, or called with. So both happen. In this case, they've all returned UTF-8 encoded strings. They both return UTF encoded strings. I'm not going to show the implementation. We don't need to see it. And here, the first example with high is just taking a plain character string, converting it to a UTF encoded string and standard string. And the second one, smile, is a UTF encoded string. It has this Unicode character in for the smiley icon, and it builds a UTF encoded string that way. I'm not going to go into the syntax of these UTF encodings that you can embed in your strings. That's not directly part of this talk, but it's good to point out that that's there. So these are the 12 overloads, all in one place. The thing to note is that for the integer, floating point, and character literals, they each take one argument of that type. And for the string literals, they take a pointer to the appropriate character type and a length. You can't go outside that list of 12. You can't define a UDL that takes an argument of int or a UDL that takes an argument of double. And don't expect the normal promotion and conversion rules to apply. If you try and use an int literal for something that's defined only for floating point, it won't find it. So if you want something that works for both ints and floating points, you need to define both of them. Same thing with characters. If you have a wide character, a literal operator, and you pass it a narrow character, it's not going to convert it for you. Let's see how we're doing on time. Not bad. Raw UDL. This one is the next step up in power and the next step up in complexity. You'll notice each one of them gets more powerful and more complex to use. Here, the UDL always has exactly the same signature, which is that it takes a car star, a const car star. It still can return any type you want. And what the compiler does is it takes the naked literal, converts it into a null terminated string, and passes that in to your UDL. So the second example here shows that this 1234.5 underscore UDL is exactly equivalent to calling the UDL operator and passing it the literal string, quote, 1 tick 234.5 null terminator. Okay? Notice that the tick gets passed through. Then the last point is actually really important. The UDL operator can parse that any way it wants. It does not need to parse it as an integer, or a floating point number in this case, if it doesn't want to. So let's take an example here. Everybody needs base 3 arithmetic, right? I mean, we're computer scientists. So I'm going to create this UDL operator called _3, which I can do because it starts with an underscore, so even though it's named 3, I can do that. And so I have my little loop here that goes through all the digits and builds a number, assuming that the input is base 3. It takes each digit, subtracts 0 from it, and shifts everything by multiplying by 3 and adding it. Okay, great. So we have our little static assert. This shows that this can be evaluated at compile time, right? And the reason it can be evaluated at compile time is because I declared it const expr. And we'll be doing that a lot. My general rule is UDL operators should always be const expr unless you have a good reason not to make them const expr. So that way you can use these things in const expr expressions to initialize a const expr variable, for example. Or if it's returning a native type, as this one does, you could actually use it in a template argument or as the size of an array. All right, and then the second example we have, we're passing 22_3, and it returns an integer 8, which is what 22 is in base 3. But we have bugs in this code. Suppose I pass in 23_3. The problem is 3 is not a base 3 digit, right? But the code merrily goes and processes it and gives you a number, returns 9. I could use a floating point number, 21.1 base 3. Doesn't make sense, but this code happily parses it. There's nothing in the definition of the UDL that says it must be an integer. And the period is interpreted as if it were a digit. So it's like period minus 0 is the digit value for that. And then the last one is simple overflow. In raw UDLs, overflow is not detected by the compiler in advance. You have to do it. So let's beef this up. We'll add the overflow detection. We'll add the out of range detection. So the very first thing we notice is in the purple that we're detecting the tick mark. And what we do with the tick mark is ignore it. Go on to the next digit. Then we detect any character that's outside of the range 0 to 2. And we say, hey, that's not a base 3 digit. And we detect that we're about to overflow. I'm not going to go into this. This took me at least half an hour to figure out the logic to say this is about to overflow, but without actually overflowing. But trust me, I tested it. And if I didn't, it's only a talk, right? I have yet to use base 3 integers. I will now. From now on, I will be using base 3 integers all over my code. But up to now, I've never used it. So if it's about to overflow, we throw an overflow. And otherwise, we do the normal logic of building our integer. Now, what do we have? Our first example, 12003, works great, returns 45 in decimal. The next one is a constexpr declaration. And when we try and evaluate this thing at compile time, it throws. And if you try and throw at compile time, the compiler says, oh, no, you can't throw in a constexpr function at compile time, so you get a compile time error. The third one is not a constexpr. It has the same problem. It has an invalid digit in there, which is the period. But here, the compiler will not complain. Instead, it'll say, oh, I cannot evaluate this at compile time. I'm going to defer to runtime. And so you will get a runtime error. Not ideal. Same with the overflow case. So what do we do about that? We would like those things to be detected at compile time. At least I would. Well, in C++20, we have a very nice feature for fixing that. And that is, instead of using constexpr, we use consteval. Now this says this has to be evaluated at compile time, and if it can't, you get an error. So now all of those runtime errors have now changed to compile time errors. Unfortunately, it's not available in C++17 or before, so you got to wait to C++20 to be able to use this, or use the next thing, which is the operator templates, which we will get into, the template UDLs operators that we'll get to in the next section. I tried, by the way, several tricks to force the compiler to give me these errors at compile time, and maybe there's one out there, but I haven't found it for C++17. Now, again, things to note, you're responsible for overflow and underflow detection. There's only one signature, so if you want to do something different for floating point versus integer, you're out of luck. You have to have, you can do something different, but you have to return one type. If we have a cooked UDL operator and a raw UDL operator, and they are both in the same overload set, and they both match, the cooked one is preferred. Simple enough. So in this case, the cooked one is the second one. It is overload number 2. And we get that when we do 123_UDL because it doesn't match the floating point one. But the first one matches the floating point cooked UDL, and that's preferred. Now we start getting into really the hairy stuff, which is the next level of complexity and power in our UDL operators. And that is that our UDL operators are no longer functions, but are now function templates. A numeric UDL function template looks exactly like this, except of course, instead of UDL, it's whatever you want to name it. It's a parameter pack of characters. If you do not know variadic templates, this will be Greek to you. But it's a pack of non-type template parameters, and the non-type type is always char. Okay, so in other words, it takes a sequence of ordinary characters from the, what do they call it? Not the execution character set, the other one, the source code, the source character set, and passes them to this operator, which will instantiate at compile time. Always instantiates at compile time, because a template like this, it takes no arguments, as you can see. It takes no runtime arguments, so it's always instantiated at compile time. And that solves the problem I mentioned earlier of how do you force all your errors to be detected at compile time. Well, this will solve it in C++ 17. The const eval trick is so much easier if you have C++ 20. Again, just like the raw case, the compiler does not do any evaluation of the literal. It just checks that it is a valid literal. That is, it looks like an integer, it looks like a floating point, looks like a string, or it looks like a character. And the return type, now this is the cool part, can either be a specific return type, or it can be some meta program that determines what the return type should be depending on what the actual characters are. So let's look at base 3 again. Here, it's the same basic logic as we had before, but I have to create these helper templates to parse my list of characters at compile time. I can't use loops. I'm using the template programming language, which is using recursion and so on. So I've got my base case, which, let's skip the base case for a minute. I'll come back to that in a minute. This is what the normal case looks like. We have our, the part of the expression that we have computed already, the part of the value that we've computed already, that's our partial. The first character in the sequence of characters is C0. And then the rest of the characters is this parameter pack C. If, now we do a compile time if here, if the character that we're looking at is the tick mark, we're just going to throw it away and recursively call this template with the partial and the rest of the parameter pack. Otherwise, we do our error detection. But now, because this is template programming, everything is available at compile time. You can use static assert. Okay? All of the parts of this, C0, 3, and 0, are all available at compile time. They're all constant expressions. Right? Same thing with checking for overflow, partial, LL max, C0, 3. They're all constant expressions, so we can use static assert. Much simpler than using throw, which we don't want to throw anyway. We want to detect these things at compile time. And then finally, our basic logic is, again, we take our partial and multiply it by 3, add in the next digit that we're looking at, and then recurse. Finally, we end recursion when this parameter pack is empty, and we just return our partial. That's what this base case is. A little bit more complex than we saw before, right? We had to change the recursive logic, we had to use the template meta programming and so on. It's exactly the same algorithm for computing base 3 and for computing our overflows and everything, but more complicated to express. All right, so now we can define our operator very simply, taking that helper function template, instantiate it, and just simply return the result. Cool? But we can do better. When you type in 1, 2, 3 in your program, you get an int, right? But if you type in this long string of digits, you might get a long or long, right? Well, let's see if we can give the same capability to our user-defined literal. We want to return an int if it fits, or a long if it doesn't fit. So what do we do? Well, the return value of our template operator, our template UDL operator, will be this conditional. It says, well, if our helper function computes a value that fits in the size of an int, an Imax, the largest int that we defined up here, then we'll return an int. Otherwise, long, right? It's using std conditional t. And then inside the logic is exactly the same. So that's the power, there's two superpowers that this template UDL operator has versus the others. One is, the main one is the one I just showed here. The ability to change the return type based on the content of your string. How long it is, what the actual sequence of characters are, and so on. The other one is less important in C++20, which is it forces everything to happen at compile time. Okay. Again, you're responsible for all your error detection, overflow, underflow. There's only one prototype, so if you want it to return different types, you have to do this fancy metaprogramming. Remember, our cooked UDLs just did this for us. If you pass in an int, you get something different than when you pass in a floating point. You can call a different UDL operator. So cooked is so much easier if you can get away with it. Now, if you have both a cooked and a template UDL, the cooked one is preferred if they both match. But if you have a raw and a template UDL, that's ambiguous. The compiler will not pick one over the other. So compared to the raw UDLs, we have the ability to change our return type based on the content. We have the ability to force compile time evaluation even before C++20 const eval. But on the flip side, it's quite a bit harder to do. Now, in the book, when we discuss this, we try and avoid as much as possible giving opinions, like choose this over that. We just sort of like lay out this is what it looks like, and you make your own decision. I'm not writing the book right now. I can tell you, don't use this if you don't have to, but there are some really great uses for it. String UDL operators are even a tiny bit more complex because it uses a fancy brand new C++20 feature, which is the ability to use structural types as template parameters. So this is what the prototype looks like, and I'm not going to go into the C++20 semantics too deeply, but this type can be any structural type. It doesn't have to be called struct type, and I suggest you don't call it that. And basically what a structural type is something that can be constructed and destructed at compile time, and that is all public. All the members are public, the base classes, if it has any, are public. It has to be, in order to be used as a string literal, it has to, the struct type has to be convertible from a native string literal type. So either from a const char star or a const char 8 underscore t star, or something like that. If struct type is a class template, not just a class, but a class template, then its template arguments have to be deducible by using CTADs, compiler template argument deduction. Class template argument deduction, which again is a wonderful feature that we added in 17 or 14? 17. And I'll show you the use here is exactly this. This is a type that matches any string type, any native literal string type. Our string literal proxy has a data member, which is an array of characters. Its constructor is const expr, as it has to be in order to be usable in this context. And what the constructor does is it takes an array of characters of some character type and copies it into our data member. Okay, these two accessors are simply for clean code, right? So how would you use this? Well, first of all, why didn't I just store the pointer? Why did I copy it? And the reason is I can't. In the constexpr world, I cannot take this string literal and store its pointer in this context. That's why not? That is a complicated story, and I don't even know the whole story. So just trust me that it can't be done. And we see an example here of using this proxy type. We're assigning it to hello, or initializing it. Sorry, assigning is absolutely the wrong term. We are initializing it with the string hello. And because we are initializing it, and because notice here we did not specify the template arguments for str_literal proxy, it deduces those template arguments. It deduces that the char t should be just plain old char, and it deduces that the length is 6. That is all the letters in hello plus the null terminator. Same thing with the next one, except this time it deduces a different character type, which is the UTF-16 character type, and the length is only 4. Now, having that, we can define, let's say in this case, 2 different IP address types, IPv4 address and IPv6 address types. And we want a user-defined literal called IP that automatically figures out whether I'm giving it an IPv4 address or an IPv6 address. By the way, this is, I think, again, I'm not writing the book anymore, I can state my opinions. This is an example of something you should not do, right? I just don't see any reason in this particular example why you need to deduce the return type. Just have 2 different UDLs, make your life so much simpler. One for v4, one for v6. Because remember, you are writing the string directly in your code. You know what you are writing, okay? So why do you need it to deduce that? Okay, so, but for the purpose of this example, we have our conditional that says if it's a v4 address, which we can do by parsing the data, and then we have our little static function here to do that, then we're going to return a v4 address, otherwise we'll return a v6 address. Okay, really, I just really minimize the logic here so you don't see the whole implementation, just the core part of what you need to know. So when we use it, we get either a v4 address or a v6 address depending on what we passed in. And yes, those are both valid v4 and v6 addresses. In purple here, the main benefit of a string UDL operator template over a cooked string UDL operator is the ability to do template metaprogramming on a value, typically to choose a different return type based on the value. Everything happens at compile time, and you can make choices at compile time. If you don't need to do this, the cooked one version is so much simpler, so much easier to deal with. The rule here for when there's a potential ambiguity between a cooked operator and the template is the reverse. And I was surprised. I think about a week and a half ago, I didn't actually know this. It's the reverse of what it was for the numeric UDL operator templates. The template is preferred over the cooked UDL. Don't know why, but that's the way it is. Okay, now we can get into how this is actually used, and I'm going to sort of run through the standard library quickly so we can see the user use cases. In the standard library, there's an inline namespace called literals, and then specifically grouped literals for things like strings and so on are in sub namespaces under that. So if I wanted to use user-defined literal for strings, I would using the using namespace directive, I would get the string literals, and I would then be able to just use the suffix s. The string literals are s for strings. And by the way, it's really basic string, so you can get either a regular std string, or you could get a UTF-8 string, or whatever character type you've got. Okay, so the U8 string is the same thing as basic string with a UTF-8 character. The string view literals are the same thing. The suffix is SV. Imaginary numbers. I, wow, it's like math, right? IF for float, IL for long double, otherwise you get double. It works for both integer values and floating point values, but it always returns a floating point complex number. The complex number it returns has a 0 real part, and the imaginary part is set to whatever the value should be. So the 4IF is simply a complex float with a 0 real part and a 4 imaginary part, but 5 minus 3.2i, again, looks like math, gives you a complex number with a real part 5 and a imaginary part of negative 3.2, and that's done as 2 steps. This is not a single literal. The only literal is the positive 3.2i and the positive 5.0, and then the rest is compile time arithmetic. Chrono has this very rich type system for describing time concepts. And it has user-defined literals for hours, minutes, seconds, milliseconds, microseconds, nanoseconds. And all of these resulting literal types are type defs, aliases for this duration template. In the floating point case, they are also returns a duration, but the duration is instantiated with a floating point type instead of with an integer type. Okay, but they're all instantiations of the std chrono duration class template. The namespace is chrono literals inside of std, but there's an alias for it in chrono. Chrono literals is an alias for std literals chrono literals. There are also 2 new ones in C++ 20 in chrono literals, one for day and one for year, and we don't have any for month or weekday because we don't use the numeric representations of those. We just have constants for Monday, Tuesday, Wednesday, and so on. All right, let's get to our use cases. I want to run by these quickly enough that we have at least a little time for questions. So when do you really want to use user-defined literals? Well, one of the purposes that you can put this to is to avoid type sinks. So here's the problem with type sinks. A type sink is a type that is so ubiquitous that it can match way too many possible ideas or concepts in your program. So we have our add to inventory function. It takes a part number and a quantity, but the part number is simply an alias for int, as we see up here. So when we say add to inventory and we pass in the part number and the quantity, great, it adds 2 units, in this case of part number 90042. And then if we accidentally reverse the arguments, the compiler will be none the wiser and just do the wrong thing, right? So we have a bug in our code, and it's a hard to detect bug because who's to say that you don't really want 90,042 items, right, of part number 2, right? And then you got this funny one here, which is that our part numbers are really maybe always 5-digit numbers. And in this case, the first, for clarity, we always put in that our 0 fill, except that this is no longer a decimal number, it's now an octal number. And we, again, did the wrong thing. So, int is our type sink. Everything is just kind of matching int. And we can do all sorts of wrong things here. So the solution is to use something that, one of the various formulations of strong type defs that people have come up with. In this case, the new makes a nice strong type def for integer-like types. So our part number is no longer an int, but it's something that's very much like an int, right? You can cast it from and to an int. But now our add to inventory function, when it says part number, it's talking about a distinct type from int. Cool. In order to make our life a little easier, we create a user-defined literal for it. And the user-defined literal in this case is a raw UDL, and it parses the string by calling str to L, always using base 10. So we're not going to get this octal problem. Unfortunately, str to L is not a const expr function yet. Maybe someday it will be. It would not be too difficult to write your own that worked at compile time and did the right thing. But for a moment, for the slideware, this is not a const expr. Okay.
C++23, 2 cars will, for ints, will be const expr.
Excellent. So which one? C++ 20?
23.
23.
2 cars. TO underscore.
Oh, two chars? Really?
Or, sorry, from chars.
From chars. Okay. Good. All right. So there will be a compile time conversion to numeric types in 23. Great. Thank you. And now, okay, our first example is the same, except now we have our UDL suffix here, part. Our second example now fails to compile because, actually, no, it will compile. This will give you a runtime error, so that's an error on my slide. No, I'm sorry, it will fail to compile because this second argument is supposed to be an int, and instead we're giving it a part number, right? And then the third one, our third example, it not only compiles, but gives you now the right answer because it interpreted the 0 as a decimal number instead of as an octal prefix. So the uses of another use case, right? Big int. We mentioned that earlier in the talk, and we could have our big int literals, and now we can describe really large integers here. Fixed point. I wish I could go into this in detail. I love this example, but one of the things about floating point numbers is that there are situations where you lose precision, especially when you're doing decimal arithmetic and you really want things to be, not to have round off errors when you say something like 0.3. Fixed point comes to the rescue a lot of the time, but the number of digits to the right of the decimal point, sorry, is, I hit the wrong button, is something you might want to determine at compile time. And in this case, we want to determine not only at compile time, but we want it to be automatically determined based on your literal. So we have a meta function called makeFixedPoint that actually computes the fixed point number and its precision at compile time. And we have a operator template that passes it to make fixed point, okay? I'm not gonna go into all the logic here because I don't have time, but our mixed fixed point is a basic recursive templates that computes not only the long integer value that's stored in our fixed point, but also how many decimal places are stored to the right of the decimal point. And then we use that in our UDL, and now we have these 4 examples where we are creating fixed point numbers. 1.2 underscore fixed is a fixed point with precision 1 decimal point to the right of the decimal point. The next one, 1.234, 3 decimal places to the right of the decimal point. And the last one, which is a valid floating point number, but is not part, but the meta program will say, no, this is we don't accept E in our fixed point representation. Other things, special string-like classes like IP addresses, right? It can check them for validity at compile time. Same thing, like here we are, our UUID. One wonderful use of these things is SI literals for like meters and centimeters and so on, seconds, grams, kilograms, and so on. And we use them in this case here where we can see what units we are and we don't end up with these unit mismatch errors that are often conversions. And if you're interested in these units, a unit library that uses these concepts, you should look at Matteus's talk from last year on YouTube, where he talks about a units library for C++ that is in the proposal stage right now in the standards committee for standardization. All right, we really need to talk about the places you can get yourself in trouble. So, does this code do what you think it does? Well, first of all, if you're using something like a raw UDL or a UDL template, you have the opportunity to parse things incorrectly. So this is the problem we showed before. If you didn't watch out for things like tick marks and periods and E and things like that, it may show up. You'll get bad values. Can you obfuscate your code with these? Absolutely. Just like with operator overloading, you can do really weird things. So this is like really cute, I thought. 192.168.0.1, except instead of dots, we're using the tick marks, and then we're parsing it. Very cute, but is that really any clearer than using a string literal for that? No, and what's worse is it looks like an integer, but it really is not, because these are octets. These are not digits in a decimal integer. Okay, so you've really obfuscated your code that way. You can build arbitrarily complex string parsing things and build little mini languages, and in some cases that's exactly what you want to do. But in many cases, just call it a constructor, pass it 3 separate arguments, let the compiler do all the heavy lifting of converting everything into integers, and you're done. Also, why are we doing this in the first place? It's to support values directly in your code. But we've been always told, don't do that, right? So here we have, without using UDLs, 0.241, which is an angle in radians. What does that number represent? Well, it represents something specific. I call it masked angle here. So nobody wants to see this code. Oh, this is an error. I should have said sign in here, but whatever. Here we're just calling on this magic number. Really, we want to give that magic number a name and use that name. Well, once you're giving something a name, the UDLs don't give you that much extra clarity. You just use the constructor directly. All right, so the same thing is true for user-defined types. Why do we need user-defined literals if most of the time we're just going to give these things names anyway, these constants? The most common use of a constant in a program is for 0 or for the null, the empty string, or for the null value or something like that. Do you really need a UDL just to be able to say 0_thing instead of giving it a name like null thing? And our signs. Notice that we have, everything has been, like for the integers, all unsigned long. And that is because there are no signed literals in C++, not even the native ones. If you say -5, what you're talking about is the literal 5 with the negation operator applied. And the same thing, of course, is true for UDLs. So you can get into real interesting problems here. Here we're converting everything into Kelvin and Celsius. We're saying, okay, if we call our Celsius function, it converts -10 here to Kelvin, which is good. That gives us the proper Kelvin number. But if we write -10C, we convert 10C into Kelvin, and then we negate it, getting something that's below absolute 0. Ugh. Okay. I have a little thing about point versus delta, like a temperature point versus how many degrees change. I don't have time to get into it here. When you get the slides, you can look into it. But chrono, for example, distinguishes a time point from a duration, and I suggest that you take a lesson from that. So now we've just got like 2 minutes left for questions. I'll let you read the conclusions on your own because I really want to be able to get to questions. And I'll be here for a little bit, and I'll be going into the other room talking to the virtual people who will have a chance to ask a question, but you in person. So any questions, comments that you'd like? Yeah, we are.
Earlier on in the slide, it said that the raw UDLs are only for numeric. Can you explain that? And why wouldn't you use that to create something that's not numeric?
You can create something that's not numeric, but the literal type, the thing that before the suffix. So the question was, why are raw literal types only for numerics, and why can't you use it for non-numeric? So you can return something that is of any type, but the syntax of the part before the suffix has to look like an integer or look like a floating point number.
So it can't be the quote.
Right. If it's a string, just use the cooked UDL because that gives you exactly everything you need. We didn't need to invent raw UDLs for strings. My time is up. Like I said, I will answer questions quickly if we can as we unpack. You have a question back there?
I noticed that if you want to it to take an integer, it always has to be a 64-bit integer.
Yes.
What about like most of the processors I work, all the processors I work are 32-bit processors. I don't want to deal with 64-bit values everywhere. Is there?
So yeah. So the question is, if for the cooked integer UDLs, it takes a full 64-bit unsigned long, which for in most platforms is 64-bit. What if I don't want to deal with the 64-bit? It's too much. It's too much. Then I have to throw bits away and so on. Well, most of the time you write your user-defined literals to be const expr. And so even though the compiler theoretically will convert your literal into an unsigned long, pass it into your function, which then is going to probably cast it back down to something like an int, like an unsigned int. Even though all of that is happening, the actual generated code, if you made it const expr, it's gonna throw all that away, and you will really only see that 32-bit thing because it's all inlined. If it's const expr, it's going to be inlined, and it'll happen at compile time probably anyway. So yes, if you have a 32-bit processor, it may look like you're doing extra work, but you probably aren't. Okay, my time is over, and so we're going to actually cut it off here. Thank you very much.